Part 1 of Unit 4 is about energy and the first law of thermodynamics. Energy is defined as the ability to do work or transfer heat. Anytime energy is used to cause an object to move, it's called work, and anytime the energy is used to raise the temperature of an object, that's energy being used as heat. In this thermochemistry unit, we're going to be focusing a lot on heat. The units of energy that we're going to be looking at as they apply to heat. First one is the joule. 1 joule is equal to kilograms times meters squared divided by seconds squared. So it's a very complicated unit that we simplify into a unit called a joule. And an older unit that still gets used sometimes as a calorie. 1 calorie is equal to 4.184 joules. Now, I know you've heard the word calorie before. It's on the back of your soda cans and snacks and everything. The calories that are listed on food are actually kilocalories, kcals, which stands for 1,000 of these regular calories. So 1 kcal is equal to 4,184 joules. So your 250 calorie Coke that you have in the morning, you'd multiply this by 250 to figure out the amount of energy that you'd have to burn to get rid of the calories from that can of Coke. The two main types of energy, potential energy and kinetic energy. Potential energy is energy that an object has due to its position or composition, and kinetic energy is energy due to motion. Now, when we say composition, that's talking about chemical potential energy. There is potential energy in the bonds of molecules. That energy is released in reactions, and that's how we have heat released in reactions. When we're talking about potential energy due to position, we can imagine a ball sitting on top of a hill. It's got potential energy sitting right here. Once that ball starts rolling, as it's rolling down here, it's exhibiting kinetic energy as it's moving. Once it reaches the bottom of the hill, can't go anywhere else, then it's going to be out of energy. All of that potential energy will have been turned into kinetic energy. The first law of thermodynamics says that the energy of the universe is a constant. That means that all the energy everywhere already exists. It's just going to be transferred between different forms. This picture was taken with the Hubble Space Telescope, and each of these points of light are a galaxy. Some are bigger because they're closer to us, but even those far off are different galaxies. Each galaxy has hundreds of millions to hundreds of billions of stars, and we know there's approximately 400 billion galaxies in the universe. So there's a whole lot of energy that already exists. We've just got to find ways to use it. Since the universe is so big, we have to come up with a way to keep track of energy so we're able to measure it. We're going to do that by identifying a system and surroundings. The system is whatever part of, in our case, the reaction that's doing something, the molecules that are responsible for an energy change, the molecules that are directly involved in a reaction. The surroundings are going to be everything else. That could be water that aqueous solutions are dissolved in, containers that reactions are happening in, the air around a reaction. It's everything that's outside of the system. So in any case, as system is the specific part that we're focusing on to measure the change in energy, and the surroundings are going to be everything else. We need to be able to track whether energy is going from the system out into the surroundings, or if the system is absorbing energy from the surroundings. Energy is what we call a state function. That means we only need to know about the present state of a system, not how it got there. That makes our calculations a whole lot easier. We can use a general form of an equation, delta E. Anytime you see delta, that means change. So a change in energy can be calculated by subtracting the energy of the products minus the energy of the reactants. since energy is a state function, we don't have to worry about how the energy changed between the reactants and products. We just have to know what the values are for the reactants and products to determine our delta E, our change in energy. Anytime that delta E is positive, that's going to be an endergonic reaction. That means that the system absorbed energy. Anytime that delta E is negative, that's going to be exergonic. That means that the system lost energy. Your question for this section: I'm cooking burgers on my C3H8 grill, that's a propane grill. Identify the system and the immediate surroundings in this scenario. Don't just say everything else.